So good morning, everyone. It's a great pleasure to be here with you, and also very happy to be in a place where it looks like so many people like B stars. There are so many B stars talks, and it's always a pleasure. I study B stars for at least 18 years now, and I work mostly on models, but I also work on observations a lot, my students and me and my collaborators. So I'm going to tell a little bit about the research we are doing, and other people, of course, are doing around the world about these guys. And the main topic of my talk is about mass laws, but I'm going to talk about other stuff as well. So I'm going to start with an introduction, since when I realized I was the first, so it's a great honor to open the workshop, this conference. When I realized I was going to be the first, I decided to make an introduction on what are B stars, where they come from, so why there exist stars that rotate so fast, right? It's still a mystery, astrophysically speaking. Why they're important. So this is also important for us to realize why that B stars can be very important in many contexts. And then I'm going to bring you news about the mass laws front, and then some news, very recent results about the disk of these stars. So I start with this image here. It looks better in my screen, not so great here. But this is, to my knowledge, the most astrophysically accurate representation of B star to date, because this is a model of Ahernar, which is the 10th brightest star in the sky. So you don't see it. I don't get to see Polaris. You don't get to see Ahernar. So I never see Polaris in my life. When you don't see Ahernar, which is very beautiful at the head of the Eridanus constellation, right? But this is it's a model of Ahernar, and why it's accurate? It's because we took our model, computer model, and we run through software to make it as if the colors are true colors. So this would be as an astronaut in Ahernar would see these colors here, which I found very beautiful, right? So, and one of the reasons unfortunately, there is a shade of green here in the poles that you don't see, but that's okay. So let's start with the introduction then. Let's put B stars in a context. So another object that you don't see much, this is the jewel box open cluster. So I don't know if any of you had the opportunity to travel to the south, to the southern hemisphere, and this is one of the most beautiful open clusters, and also it's one of the youngest. It's only 14 million years old. It is like very, very young, right? And it's a very common target for amateurs when you have star parties, because you can see it with your naked eye. It's Kappa Crucis, very close to the Crux constellation. But when you see in a telescope, it's just beautiful. That's why it's called the jewel box. And then almost all bright stars that you are seeing here, almost all of them, but for 3, they are B stars. B stars. And some of them are BE stars. I'm going to show them, right? So what are B stars? They are massive or intermediate mass. So some of them are very low mass, 3 solar mass. Some of them are 20 solar masses, right? Luminosity range between 200 and more than 50,000 solar luminosities. So what I find strange about B stars, not BE yet, is that you put a lot of different things in a single bag, right? They're very different. They're completely different, evolutionarily speaking. Their structure is different. Everything is very different. And still you call them by the same name, which is kind of bizarre. But that's how astronomy works sometimes. So this is the famous HR diagram. So if you don't remember, so here is plotted the color or the temperature. So red, blue, and then very luminous, not so luminous. This is magnitude, of course. And then here are the B stars. All of these bright guys here are here, right? And of course, these three little red strange guys here are the B stars. Perhaps this one I didn't check. And this yellow guy here is this guy here, which is the only evolved object in this cluster so far, and that's because it's so young, right? So why I'm showing this to you? Well, it is nice, but also this is the kind of main sequence. If you remember, main sequence is this strip here where all stars are. All of them are burning helium, hydrogen into helium in their first phase of their life. So this is what we call in astrophysics a simple main sequence. So if you go to textbooks and courses and you learn about main sequence, it's always a line, isn't it? Or a strip. But reality is very different. When you start looking at main sequence in detail, then you started in some clusters you start seeing some things very strange. So not all main sequences are so simple, right? And here are a few examples for you, right? Of very complex main sequence. All of these are in the Magellanic Clouds, which you unfortunately can also, you have Andromeda, we have the Magellanic Clouds, right? Basically. So there are several open clusters in the SMC, and you see many strange things. If you start looking in detail, you see multiple main sequence. It appears to have one here, another here. If you look carefully here, there is a line here, and then there is a bunch of here. So we started seeing multiple main sequence. You started to have extended main sequence, they call. So if you remember, stars that are leaving the main sequence are old enough to have evolved. So they're moving towards the red, super red, in this case, right? Red phase, red supergiant phase. And then, but why are these guys here? There are so many. So they should not be there. So textbooks forbid them to be there, old textbooks, right? So an extended main sequence. Uncertain turn-off points. If you remember what turn-off point is the place in the main sequence where stars are evolving and leaving the main sequence towards other phases. And we call it the turn-off point, and that's how we measure the age of a cluster, right? And then uncertain turn-off points, you cannot even know what they are. And this has been, in the professional domain, people that study populations and stellar evolution, this has been a very hot topic. If you look, there are tens of papers in the last years. Lots of papers dealing with this, because all of a sudden it became an interesting problem, right? Why? For me and for us, it is interesting. Because the causes for this, I'm going to talk a little bit about it, is binarity. We are finding that perhaps all B stars are binaries. There is one, at least to my knowledge, one exception to this rule, which is not true yet. It's Zahernar, which is binary, but it's too far away, right? So all of them are binary so far. And also, all of them are fast rotators. So fast rotation is also causing this extended main life. So B stars are part of the explanation for this very complex behavior we see these days in open clusters, right? And of course, the red dots here, I didn't mention, but the red dots here are all thought to be B stars, but they're not proven to be B stars, okay? Okay, so since we are talking about B stars, what are they, right? They are fast rotators. There is no exception to this rule. So these are B stars that rotate very, very fast. So all B stars rotate very fast. BE stars rotate very fast, but not all B stars, B, that rotate fast are B stars. I don't know if you got what I meant. Okay. They are fast rotate. They have three ingredients basically. They possess a disk. So this is another image of my radiative transfer code showing a model of the disk around the Zeta Tauri. In this case, this disk has a spiral arm around it. So it has, you can see the spiral arm and it's seen from the side. This is the same model of Zahernar that I showed before, but this doesn't have the true colors, just representation of how Achernar would be seen at different viewing angles, right? From the pole and from the side, you can see the disk around it. So they sometimes possess a disk, sometimes, and all of them are radial pulsators. So this is a very technical thing, but it is now 100% certainty that all these stars pulsate, all of them. But they don't pulsate radially like the Cepheids do. They pulsate non-radially, so they have waves traveling in their surface, basically. That's the radial pulsation, if you want to think about it. So I'm not going to talk much about pulsation, just a little bit, right? And since you are in a spectroscopic conference, spectroscopy is historically, by very far, the main source of information about the star and the disk. So if you want to learn about these stars, you have to understand the spectroscopy, because that's how they've been studied. In the past, polarization, light polarization, photometry also important, interferometry is also important, and of course, recently, space photometry, photometry done in space is very important. I'm going to show you many results of that, right? Okay, let's talk then about the central star. So there are B stars, as I said, but one of the key questions is, and I'm sure that I'm going to have people here in the audience that's going to disagree with me, I believe they are all main sequence. But some people believe they can be post-main sequence. And I think that cannot be, but is open to discussion. But in general, they are main sequence. They are there in that strip there, the main sequence in the diagram. So as the most rapid rotation known to exist, they're normal stars. When I talk normal, I'm kind of excluding white dwarfs and the neutron stars. So if you exclude those, they are by very far the fastest rotators known. And this fast rotation causes them to be geometrically flattened, so they are very flat, like this. It's an oblate shape. You can see this in this animation here. Gravity darkening is a very interesting phenomenon. When you rotate very fast, because of gravity darkening, flux leaves the star more easily, say, through the poles, so the poles become very hot, and the equator becomes very cold. And the difference can be very large. So a star may have 25,000 Kelvin in the pole, and it can be 15,000 Kelvin or less in the equator. And you can see the gravity darkening a little bit here too. And I'm not going to say much about internal coupling because it has to do with stellar evolution, but the fact that they rotate, it's like a blender, if you want. Like stars that are normal, they are just sitting there, nothing is happening. But these stars rotate so fast that they start to mix together internally. And this is a very difficult problem to solve. Not too far away here, you have like the people from Geneva Observatory who are world leaders in models of fast rotating stars, and they still don't have an answer for most of the problems, right? So it's very complex. And of course, they are very different. They're very different from normal B stars. So the huge difference between fast rotators and the star that doesn't rotate so fast. Okay, so how fast they rotate? This is a sample showing this line here is what we call critical rotation. So what happens if a star rotates so fast that it reaches the critical rotation in astronomy? It starts to break apart. It rotates so fast. It's like, for instance, if you have a bucket, and if you spin it too fast, the water is going to start spilling over. So this bucket it's not full to the brim, right, the bucket. But then you start spinning it fast, and then it's going to start spilling over all over the place. So that's what happens. So you can see that they are very fast. Some of them are rotating very close to the limit. And some of them, at least what has been measured, is above the limit, but this can be argued that's probably an incorrect measurement or something, right? And here is a comparison between a star that doesn't rotate so fast, it's still a B star, and this a one that rotates very fast. Look how different they are. This is very flat, not so flat. You see the cold equator here? Here is the temperature actually. See how cold the equator is, and the pole is very, very hot. This is not so extreme here, right? So you can have a comparison here between different rotation regimes, but all of them are still can be rotating fast enough to be a B star. And I'm not going to talk much about these, so don't look much at the plots because they are not very beautiful. But what the plot is telling you is that sometimes you see here the line 40%. What's the plot telling us? Because they rotate fast, sometimes they can live 40% longer than a normal star. Because of internal mixture and other phenomena, do you remember that I told you that they mix? So what happens is that when they start mixing fuel from outside, it's going back to the core of the star and rejuvenating the star. So they have like a use fountain, if you want. Rotate faster and they live longer, right? Which is important, and that's one of the reasons why you have extended main sequences. The normal B stars are already leaving the main sequence, but the B stars are there still in the main sequence. There are other factors too, right? I'm going to jump that. Okay, what is important for us, and Manfred already mentioned this, they are quite common. Why amateurs love B stars? Because there are gazillions of B stars in the sky. And you may ask yourself, how common they are? They're pretty common. And I think all the numbers here that I'm giving you are underestimated, right? So in the galaxy, 5 to 20% of all B stars. And in the SMC, 50%, half of them. And I think this can be close to 80% in some cases. So look at this. This is a paper that it was accepted last Monday. So 3 days old. It is in Astro with my collaborator Felipe Navarrete. So this is the NGC 330 and the SMC. It's a pretty famous open cluster, very well studied. Look at, I'm going to switch the image now. So this is a composite image of B, V, and I. So you have the blue guys and the red guys there. Now I'm going to switch. Do you see? I changed it. I made B, R, and H alpha. So do you see the pink guys? Can you see it? Lots of pink guys. All of them are B stars. Look how many there are, right? Look at this. A lot of B stars in these young clusters, right? So sometimes even 60% in some spectral subtypes, right? And now I can show you this. This is from that paper, Navarrete. And look at the B2 stars. B2 stars are 13, I think 12 solar masses or so. So they are not so hot as the B0, but they're much hotter than the others. Look, estimated 60%. And this is a lower limit, right? I can discuss later to you, if you are interested, why this is a lower limit, right? Anyway, now I'd like to talk a little bit formation scenario. So the question is, how can you form a star that rotates so fast? That's a very interesting problem for which astronomy doesn't have an answer, right? Because it's very complex. There are three possibilities. So the question is, why in some cases, like for instance here, why in some cases you do have normal B stars? The blue ones are normal B stars. They are not doing nothing. But why in some cases you form stars that are very fast, right? So one of the main scenarios is that, okay, they are born this way. I don't worry about this. But this has problems. I don't have the time to talk here about theory of mass loss, of star formation. But there are questions. We don't know the answers as to why both of the observations or models are quite certain. One thing that is important is there are B stars even in the youngest clusters. So do you remember the youngest, one of the jewel box that I showed? 14 million years. It has B stars on it. So some B stars are already born B stars, that's for sure. Okay? The other one is what we call evolutionary spin-up. So as the star evolves in the main sequence and becomes an older star, it's still main sequence, but it's evolving. Model suggests that it starts to rotating faster, right? And this is what is being shown here. You have stars that start already fast, but then they rotate faster and faster and faster, suggesting that when they are getting to the end of the main sequence, they may become a B star. This is probably happening, but for many years, people believed that was the only explanation, right? But of course, one of the predictions of this model is that because the star becomes faster and faster and faster, if it becomes a B star, it's going to become a B star forever until it leaves the main sequence. However, there are some results showing that the fraction of B stars, this is age. It may peak at a given age, but then it can get lower again. So there are possible explanations for this, but maybe there are B stars that become B stars and then they are not B stars anymore. And then this evolutionary spin-up is a problem. And now my favorite one. My favorite one is the binary evolution. So I'm going to show you a video that my student made. And please, it is very crudely made, okay? So there's a big disclaimer here. This video is very astrophysically inaccurate, okay? It's just a toy video, okay? So what happens is that we start with two stars. You start with two stars. They're binary. One of them is slightly more massive than the other, a little more massive. Say, 20 solar masses and 15 solar masses. The 20 solar mass one is going to evolve first and become a supergiant first, right? And then that's the phase that starts. You have a normal star. Something happens that the star starts to, the primary starts to transfer mass to the secondary. And when this mass transfer happens, it is not only mass, it's angular momentum, how fast the star rotates. So you start this crude oops, it's going to start at one moment. Okay, we start with a normal star. Here's the secondary, but because it gained so much, a little mass and a lot of angular momentum, it becomes the central star. And what's left here is what we call a stripped star. A star that has been stripped, naked, right? And we see, oops, okay. And we see those things in real nature, of course. Okay, so the secondary here, which is the mass angular momentum, evolves to become a fast spinning star, and the primary evolves to become a subdwarf that we call. SD means subdwarf, which can be an O star or a B star, right? And the system ends having nearly circular orbits. And for instance, there are over 20 systems known. But there are hundreds of B stars, thousands of B stars known. Why so few? Why so few? Because well, there are many answers. But one of the answers is that it's very difficult to observe these guys here. When they are in this phase here, when they become very small, it's very difficult to observe, okay? But we have observed them, right? So where they come from? Either they are born as fast rotators, or they become fast rotators because they spin up, or they are a result of binary evolution, right? So the truth is like a combination of this process. And this combination of things is what makes those complex main sequences that I showed at the beginning, where you don't have stars evolving like the normal non-rotating stars. They have their own path. So B stars are very different lives than normal B stars, okay? Okay, so let's talk about the disk itself. So this is my area of specialty, and where the disk comes from. That's one thing that we are pretty sure. It comes from matter, from the star itself. So do you remember the bucket analogy? If you rotate the bucket too fast, it starts to spill all over. So these stars are that. They are spilling all over. They are just sending matter out. And these matters, we don't understand the physical process that lifted this matter yet. I'm going to discuss this in this talk, right? What the most recent results that we have. But what we know pretty sure, and this part here, is that through a mechanism called viscosity, right? Through a mechanism called viscosity, this disk grows. So what is viscosity? Let's suppose that I open a bottle of perfume here for you. Okay? You are here sitting, and then I open a bottle of perfume. It's going to take perhaps a few minutes for you to start smelling the perfume. Close here, farther away. Now, if you make a calculation, how long it takes for a molecule to diffuse, so one molecule of perfume hitting the other molecules and reaching you here, it takes years. It takes years. So how come a molecule, you can smell the perfume in 5 minutes or 30 seconds, depends on where you are. Do you understand the problem? Molecules takes a long time to travel, but the perfume arrives. It's because this is a complex atmosphere. We have vortices, right? We have vortices going on. You have air, and these vortices create what we call abnormal viscosity, which makes transportation much faster. And that's what happens with B stars. They have these vortices in the disk that allows them to transport matter, and they become, the disk can grow very fast. So a B star can form a disk almost as big as the solar system in a few months. Isn't this amazing? The disk is almost as big as the solar, not the solar system, the inner solar system, say 2, 3 astronomical union, if you want, unit, in a few months. How amazing is that, right? It's all of this because of viscosity, right? And then these days, I'm not going to talk about this model because it is technical stuff, but we have this model, it's called the viscous decretion model. Why decretion? Because the contrary of accretion. The model is B stars are decreting. They are not accreting matter, they are decreting, they are expelling matter away, right? Okay. So, and they are intrinsically variable. So if you observe a B star in photometry for long enough, so these are photometric measurements of a B star in the Magellanic Clouds. What it does sometimes is this. It's doing nothing. All of a sudden it becomes very bright. Almost 1 magnitude, see? No, half a magnitude in this case. It's a 0.6 magnitude, but very bright. And then all of a sudden it reaches a maximum and then it dissipates. At the same time, the star is becoming redder, brighter and redder. So if you see this happening in data, this is a disk that is growing and dissipating. In this example, the disk took 1,600 days to build from here to here, more or less. And then it took almost 14 years to dissipate. Amazing, isn't it? So it's a very long time. So, and this is not an uncommon thing. I have a student that's finishing a paper now with 4,000 light curves. He took 2 years to analyze 4,000, poor guy, right? 4,000 light curves of B stars. And that's very common. That's how we see this day happening in. Then we call this outburst. Outburst, which is like out explosion, so it's active, it's forming the disk. And we call this part dissipation, which is just the disk that is leaving or being destroyed, okay? Now, sorry, I tried to make a video, but I could not. So this is a very ugly picture, sorry for that. But this is from the best database of one of my favorite examples, QRVU, showing disk formation also in spectroscopy. So you can see here many years, like, I don't know, 12 years or so, Disk forms, dissipates, forms, dissipates, forms, and I don't know what's going on. Perhaps it's doing nothing?
It's already in absorption.
Already in absorption. So we have so it's not only me that likes this guy. And then you see all sorts of very complex spectral profiles that I'm going to show in detail later for you. So how a BE disk is formed. So sometimes I find these videos nice. So what I did was to take our models. Our models combine hydrodynamics, so we calculated the equations of fluids and everything, with radiative transfer, so we can make models of the B star growing, dissipating, these kind of things. And I like to show these videos here. So this is a B star that's in pole on. Pole on, you're seeing the pole towards you, right? And then what you see, this is the light curve. It grows, brightens, deepens in a very complex way. This is a model, okay? But then you can see what happens with the disk here. So it starts with no disk. So this is the end, right? It's going to play over again. There is no disk now, but then it starts with no disk, and then the disk grows and dissipates and grows and dissipates. And this is seen from the side, very nice. It looks like Saturn a little bit, right? Very, very flattened, bright poles, as I said, and you can see the disk. In the case when you see from the side, the star becomes fainter because the disk is obscurating the star, right? Now, that's very important. So people are very confused with this sometimes. The disk grows from inside out because matter comes from the star. But the disk dissipates inside out too. Why? Because the inner disk, once matter stops being lost, the inner disk loses support from the star and it starts falling back. Right? It starts falling back to the star. And that's what happens. So it dissipates inside out, but it is carved inside out when it's dissipating. So it grows inside out and it's carved inside out when it's dissipating. So this plot here, this is what's going on for the same light curve. This is the model. You can see here now how the density evolves. This is a cut of the density from the side. And this is the mass loss. So zero mass loss, turn on mass loss, turn off, on and off. So this is just a toy model, right? Just to show that we can reproduce these effects these days. Here is a simpler example, what we call isolated disk event, where this one is similar to the one I showed you 2 slides before. So it just forms a disk and dissipates and nothing fancy is going on, very difficult. In this case, all you have is the mass loss is on and then off again, right? So why fitting disk event? So this is a real disk event and this is our models, right? This is a former PhD student of mine and this is our model. So why modeling this disk is important? Because we are measuring the viscosity of the disk for the first time. Viscosity is something very complex in physics. There is no theory of viscosity yet, right? There is no theory of viscosity that everybody is happy about. And we only exists because of viscosity. Viscosity was a major thing in the disk that formed Earth. If there was no viscosity, there would be no Earth. So we exist because of this, so let's measure it, right? And try to understand it. So here it just shows, okay, it doesn't matter very much, but it just tells us that we can do these kind of things these days. Okay, this was the introduction. If anybody has a question, can ask, I guess, or we can just move to the mass loss. So I came here to talk about mass loss, right? So let's talk about it. Okay. This is a complex plot, but what is going on? Since 5 or 6 years ago, there is a new toy floating on in space, which is called TESS. TESS is a NASA observatory that wants to that the goal is to hunt for exoplanets, Transit Exoplanet Survey Satellite. That's the name, right? But we, B-star guys, we are using the data a lot, right? Because the data, it's absolutely very, very precise. It's 50 parts per million photometry, which is amazing, right? Then, this is a B-star, JSON, right, observed in photometry. So what is this? Look that this is days now. Before, we are talking about the evolution of the disk in years, right? Now this is days. In a few days it rise up, became brighter, and then it went down, and there was these flickers, outbursts and stuff. So when we started observing B stars with stats, we realized that they are very active and that they are losing matter all the time, but not continuously. They are losing a little bit every time. It's not a continuous flow of matter. They just lose matter all the time, continuously. And that's due to pulsation. So one thing that we can say for sure is that pulsation in B stars is what's driving the mass loss. Why can you say that? This is pulsation here. Do you see this oscillation here? This is the star pulsating. And when the pulsation becomes larger, more intense, mass is getting out and the disk is being formed. Every time there is a mass ejection, every peak here is a mass ejection in a B star, happening every few days. Every time there is a peak, there is a mass ejection, and every time there is a mass ejection, there is enhanced pulsation. Cool, huh? So we could only see this from space. So we know now we don't know anything about pulsation. There is no theory of pulsation. So I just come here and say the many things that we don't know. There is no theory of pulsation that's advanced enough for us to do these calculations yet. But we know that's pulsation, okay? And that's it. So the main result, mass loss or mass injection into the disk is unequivocally related to pulsation. That's a lesson that you can take if you want. B stars only are B stars because they pulsate. If they didn't pulsate, they would not be B stars. There are B stars that rotate very fast. They are called the BN stars, but they never produce a disk because they don't pulsate. Interesting, right? So we learned something. Okay, now space photometry. So if we have this guy, space photometry is so sensitive, so we don't need anything else, right? You'd say, okay, you don't need any other information. No, because photometry tells basically how much material there is. So if there was a mass ejection, the star is going to become a little brighter, but we don't know where this material is, we don't know the geometry, we don't know the kinematics, how fast this material is rotating. It's completely blind to these things. Spectroscopy is the tool that we need, right? Because, so I don't know if all of you have seen things like this before, but imagine that you have a disk. The star is here, this disk is rotating like this arrow here. And you are observing. Everybody knows, so you've probably seen before, that a B star is going to have a double peak profile because of the rotation. The double peak happens because the disk is rotating. And what happens is, if you look, the portion of the disk shaded in blue here is responsible for emission in these velocities here. The portion of the disk shaded in red is responsible for this part, in purple and in brown. The thing is that spectroscopy allows us to map the disk, tell us where emission is coming from. That's pretty important. And TESS cannot see that. So we need to combine the two. We need a combination of the two. And what happens when you have a complex disk? Because this is a very smooth, beautiful, theoretical disk. But if you have a complex disk like this one, which is a simulation I'm going to show you later, the profile becomes very different. So as the observer is here in this line, so the observer is traveling along this line here, and then you have those maps that I showed you before, and those representation here showing that the profile is going to become very asymmetric over time. And that's what we want to study. And that's why spectra is so important, right? We call these things V-ONR variations because this is just the violet peak and the red peak is becoming with different heights. That's what we call VONR variation, right? And then we started the Frisbee project. We like, astronomers like very silly names, right? And the Frisbee project is following really intensively spectroscopy BE emission events, right? So we involved lots of amateurs in the community. This was led by a collaborator of mine. He was my former postdoc, Jonathan Labadie-Bartz. And then he's in contact with many amateurs via BESS, the BESS database, the BESS forum. And many people are observing, and you are going to see why it is so important, right? I'm going to show you, okay? So what's the strategy? We took all the stars that TESS was going to observe over 4 or 5 years. We're talking over 1,000 stars, right? And then select stars that are active. So historically, we know the ones that are very active and the ones that are very boring. There are boring B stars. Beta CMI. Imagine a boring B star. It does nothing. It has the same disk for 100 years. I don't care about beta CMI. No, I love beta CMI actually. But it's important for other reasons, right? But we need the active ones, right? And then we monitor every night with spectroscopy and analyze data immediately. Why? Because if you sleep on the data for 3 days, you lose your opportunity. And then when the spectra show mass ejection, increase cadence. Sounds difficult, right? We've been working very hard on this, but after a 4-year-long effort, we have 13 B stars with well-documented cases of mass loss, both in TESS and spectroscopy. And the paper is being written at this moment. It's almost done, so it is very new results. Nobody saw it yet, only me and Jonathan, basically. Okay, here is the results. I picked three stars to show you, okay? Because they show different examples. This star here, V767 it had a very, very strong disk previously. So this is one case of the observations, right? This star, F-car, is our new favorite star. This is my favorite star, F-car. Because it started with 0, nothing, and then formed a disk. And we could see it with TESS and spectroscopy. And there are some complex variability too that I'm going to show. So, of course, it's very difficult to understand this plot. What is it saying? It's all the spectra that we have obtained during the test, showing lots of variability. 2 spectra were chosen just to show how they can vary from one night to the other. One night to the other, look. One night to the other here. And that's how variable these guys are, okay? So let's start with F-car. F-car. F-car in TESS, F-car did this. Boring, 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 boring. What is this wriggle here? Pulsation. It's just pulsating. All of a sudden, it decided to do something of its life. A small blip. And then a large one, right? Followed by a large one. But it lasted a few days only, as you can see. Now let's look what spectroscopy tells us, right? Oof, complex, huh? I'm going to show a better plot. But see, the first is just telling us that there is nothing going on. Very small activity related to pulsation. So this variability here in the line profiles, this is H alpha, okay? It's pulsation. But then the disk starts to form here. You see? From one night to another. No disk, disk. Amazing. And then it grew, and dissipated. So this that we are seeing, this here that I'm showing you is this here. This way. Up. It is how time evolves, right? So, very complex. We decided we have to simplify things a little bit, right? So we started making measurements on these lines. The first measure is the equivalent width that you probably know what equivalent width is the area under the curve. That's the equivalent width here. Total emission measure. The VONR ratio it's very used in astronomy in B star, which is the ratio of the violet peak and the red peak, very important. However, what do you do when you have multiple peaks? It's very complex. So we decided to explore something, Anatoly and our colleagues here, that we've never seen in the literature before. It's kind of interesting. You first find the systemic velocity, the center of the line, and then you calculate the equivalent width in one side, the equivalent width in the other side, and you ratio it. And it became a beautiful measurement of asymmetry, very useful for us. And this is the result. So here you can see the outburst. So the star is exploding, and this is what happens with H alpha. Look, we have spectra every night, and some nights many spectra. Unfortunately, we have daylight that creates these gaps in the data, right? But look, one of the things is that you see that in photometry, the disk grows and dissipates very fast. In H alpha, no. It grows, and it takes weeks and weeks to dissipate, but it takes days to dissipate invisibility. So we can explain this because of optical depth effects, these kind of things, but it is very interesting to see this happening. But what's the most important for us is this. This is the line asymmetry. So do remember this definition here, the equivalent width of one side, the area of one side divided by the area of the other side, right? And then you plot it, and something very interesting starts to happen. And this is true for 100% of the cases. Every time mass loss is happening, every time, the equivalent width of H alpha, the asymmetry, is very large and periodic, with periods of about in this case, 1.7 day. You can see the period here. It's happening. Every mass loss. But it also dampens over time. So two properties. It is periodic, and it is also dampening over time. Dampening is like vanishing over time. Why is this happening? I'm going to show a model of this in a few slides, okay? So just hold this information for the moment. So highly asymmetrical and periodic. So this is the result for FCAR. I'm going to skip that. And this is the result for this star V767SEN. It started already with a strong disk. So we had spectra before TESS, and it had a huge disk already. And then the details are different in the sense that you have a very complex things going on in photometry. You can see that the H alpha is always delayed. So if the disk starts to form, and then H alpha goes later. It's the same. It's always the same. H alpha is always delayed with respect to photometry, right? There is a reason for that. But then what's important for us in the context of this presentation is asymmetry. The same kind of asymmetry. This kind is a different period, faster. It is about 0.8, say, cycles per day. It varies, right? But it's very fast. It's happening in less than 1 day, right? But it is there. And now the last case, 12 Vulpecula, which is very complex. 12 Vulpecula, at least in what we are seeing, seems to be losing mass almost all the time, right? And one outburst on top of the other, see? You have an outburst, and then you have another one, and then another one, happening at the same time, on top of the other. This causes a very complex line variability, difficult to interpret and everything, but the asymmetries are there perfect. Every time there is an outburst, every time there is a line asymmetry that varies cyclically with a period, in this case, 2 days. It varies between 0.7 days to 3 days maximum. So when you look at the full sample, so what we are seeing here is the frequencies here. The blue ones are photospheric frequencies. What are photospheric frequencies? Pulsation. So the blue lines show the frequency that the stars are pulsating. In this case, two cycles of pulsation per day, 3 cycles of pulsation per day, 4. You see, they pulsate very fast, but the oscillation of their H-alpha is lower. So this is the H-alpha oscillation, always smaller than the pulsation period, and this is exactly what we expect. We expect that the pulsation periods happen on faster than the H-alpha. So in red, the H-alpha symmetries indicate circumstellar origin of this, which is very interesting. And you see, there is never a strong peak here, so we are talking about different things. This is not happening at the photosphere. This is happening in the circumstellar level, okay? So, conclusions of the Frisbee project, okay? Paper is coming out very soon. We identified 13 stars, but we measured 15 flickers. Flickers is an event of mass loss, 15 well-documented flickers. 100% of them, there is not a single exception, showed strong asymmetry that is cyclic and dampens. Always the same behavior, right? Therefore, in all cases, and that's a very important conclusion, we don't know how B star lose mass, but we learned something very important from this study. And this thanks to many, in these spectra that I showed, lots of amateur spectra, lots of them. And the only reason we can conclude, we could reach this conclusion is that we have so many spectra, right? And the conclusion is B stars do not lose mass in a very smooth way. It's in a catastrophic way, in an asymmetric way. It is always localized on the surface, always. B stars lose mass in a concentrated way. Okay, as we started learning this, I took one of my PhD students, Amanda Rubio, took her and said, "You're going to work on this project. Let's understand how this happens," right? And the idea here is the following. You have a rotating star, okay? You have a rotating star. And you have a point on the surface of this rotating star that's losing mass. So the star is rotating, right, like this. So if mass is directed in the direction of rotation, what happens? Velocities add up. And then you have a large velocity. And then this material enters orbit. So it's an explosion happening on the surface, like a grenade. Imagine a grenade. It's an explosion. Something is kaboom there. Part of the material is going to be in the direction of rotation. So it's going to add up the velocities. And then you are going to enter orbit. Part of the material is moving in the wrong direction. And it's going to have a very small velocity, is going to fall back to the star. This is called a Crow's gravity filter because a German guy, Crow, I forgot his name, he defended a thesis in the 90s where he put this idea, but he never published it. So, okay, let's keep the name, Crow gravity filter, and let's do it. And we did it. And this is the first SPH simulation. So what's that SPH? SPH is a technique in numerical calculations where we solve the fluids, complex fluid patterns, by simulating many, many particles. So we make the fluid discrete. So that's called smoothed particle hydrodynamics, SPH. Okay? And then that's the thing. We started losing mass at one point. I cannot come back to the beginning of the movie, but it's going to play itself again. So let's wait just perhaps a few seconds. And then I'm going, okay, injection. And then matter is going to, so this is the star rotating. And then as matter is being lost, then you start forming an asymmetric disk. But then, now mass loss is turned off. And this disk starts to rotate and smooth out. So you start with a symmetric disk, and then this disk smooths out. Exactly what we see in the observations, because in the observations we see it starts with high asymmetry in the lines, and this asymmetry is periodic, exactly following these things here. It's periodic because the star is rotating, right? But then, as mass loss stops, the material starts to smooth out and circularize, and asymmetry goes away, right? So this is a model, and these are H-alpha profiles from that model. So it's still being written in the paper, but these are real data. These are models for FCAR, and this is real data. This is model, not too bad, right? So we understand things how it works now. We now can say more or less that we are at least a little, one step closer to understand how mass loss is happening on B stars. So that's the conclusion. So do I have 10 minutes or should I stop?
10 minutes, okay.
Is okay? So I want to change topic. It's not the topic of my talk, which is the mass loss front. But I like disks a lot. Sorry, Miroshnichenko, you're going to talk about disks, but I'm going to talk about disks too.
Just complete your talk.
Okay, let's complete each other talk. So I like to bring some news about the disk front, because we have been uncovering some stuff very interesting, thanks again to spectroscopy. So I tried to mold my talk to say where is spectroscopy, why it's so important, where it is playing very important role in B star research, right? So news from the disk front. Most disks are quite different than this. So this is a simple model, very smooth, very idealized. You know the joke about the spherical cows? Have you heard about this joke? No? So this joke, there is a joke that says that there is a farmer, and this farmer is having problems with the cows, the milk production. And then he calls all sorts of specialists. One of these specialists is a physicist. And there is also a veterinarian and all that. And then they go there and they visit the farm, and the physicist says, I have a solution for your problem. And the farmer gets very happy, right? But this solution only works for spherical cows in the vacuum, right? That's the joke. So we make these models in a very idealized ways. So this is a spherical cow model, say. Real models of real nature are much more complicated. Now, look at this. You are spectroscopies. And, okay, this terrifies me. I have some sleepless nights of this because of it. I'm kidding. But it's very scary. This is a B star that we discovered. No, it's not discovered, sorry. At least the nature of it is being explained by a paper. It was discovered by another person, but this person didn't provide the correct explanation for the nature. Anyway, this is this guy here. And it is in a binary system with 31 days period. And this is showing the spectrum as you have one picture, one revolution, one full revolution, showing how complex it is. And we have the model. So what is going on here? Let's see the models. And these are the models. The observer is here on the top. So your top is there in the A looking down. And then you have the center star here, and you have the secondary star here. And you see that the disk becomes completely a mess. These are models. Why? What's going on? Right? Because the secondary star is so close, 30 days, it's very close. I would say it is about 40, like a fifth of one astronomical unit, more or less. Unit, sorry. About the orbit of Mercury, I'm guessing, more or less like that, right? And then very close to the central star. So gravity of the secondary is important. If there were no secondary, the disk would be very smooth, very circular, very boring. But no, there is a binary, and it is mixing up the disk a lot. So let's study this. So these are models that we run, SPH models. How the models start? They start with a star, the B star, the secondary here, with no disk, and then this disk starts to grow and grow and grow. all of a sudden something very interesting starts to happen. Material from the disk starts to spill over the secondary. You can see. Material starts to be swallowed by the secondary, attracted, say, by the secondary. And if you leave this simulation long enough, what happens? So this is the beginning of the simulation. Now, if you let the simulation run for several months in physical time, right? Here's what happens. This is a real BE disk, actually. Because a BE disk, sorry. This is a real BE disk. A BE disk that has grown enough, it starts to spill matter over what we call the, sorry. I'm pressing the wrong button here. This is the so-called Roche lobe here, and matter starts to flow onto the secondary. And part of it is absorbed by the secondary, and part of it leaves. So we learned something new today. Another something that probably, this has not been published, so nobody knows yet, which is how B star loses mass to the interstellar medium. They don't lose mass in a symmetric way. They lose mass via the secondary. The secondary is slingshots the material and accelerates the material from far away, and that's how B star lose mass. This shows a full simulation now. This is just here. Look at this inner part here. This inner part is here. So this is what we call the disk. Then there is a secondary disk here. And then the simulations are predicting that a spiral arm that's forming around the primary is a circumbinary disk. So our simulations show that instead of having a simple disk, B stars in binaries, we identified five regions. What we call the inner disk. The inner disk is very smooth, very symmetrical, beautiful inner disk. Nothing much happens there, right? Then there is an outer part. Do you see a spiral arm here? Can you see it? There is one and another one. This is here what we call the spiral-dominated disk. The spiral-dominated disk is what's causing that line profile variability that I showed in the video. The Vionar asymmetries are being caused by this spiral-dominated disk. Then there is a structure here that we call the bridge. The bridge is starting here, more or less, is where material is being accelerated to large velocities. I'm talking almost 100 kilometers per second. That's very large. Kilometers per second, right? Velocity towards the secondary, forming a circumsecondary region, which is in blue here. And from this circumsecondary region, there is another arm that emerges and starts to wrap around the secondary. And this matter here is lost. It's never going back to the star. It's being lost by the star for good. Okay? And now, an ongoing research is, what is the role of each part? So you can see now each part, the spiral-dominated, the bridge, the circumsecondary region. Each one of them has a role in this profile here, right? And what is the role of each part in the disk? I'm not going to provide the answer because I don't know yet. Models are being run this week, actually, and perhaps in 2-3 weeks you are going to have some news where we are trying to map in the line profile where each region is originating, which is kind of nice, kind of useful, which adds value to the data where that you can study different parts of the disk with the data. So just my last 2 slides, sorry for that. This star here, V658 Car, is something that's news. So, and it is a very new kind of object for us, because it is a B star in a short period binary, 30 days, but it's seen exactly side on, exactly 89 degrees to be frank, to be exact. And because of that, this star is an eclipsing binary. So it's a B star eclipsing binary, where you see the eclipses here. They are stellar eclipses. But those guys have disks, don't they? They have disks. And these are what we call disk eclipses, where the star, so for instance here, the eclipse 1, you see? So the observer is here, eclipse 1 is this guy here in red. So it's seeing the primary kind of covering the secondary, right? That's an eclipse. However, the secondary, the light from the secondary is passing through the disk. And the disk is absorbing this light. And this is causing this. Nice, isn't it? So very rare. Now we are hunting the literature for objects that are similar. We found 2. And then the question is, why so few again? Because there should be a lot of them. But there aren't. I don't know why. There is no explanation as to why. Anyway, you have these broad eclipses here. And this is my last slide showing that we can model those things. So we picked this model here. We plugged this model, we plugged this model here into a radiation transfer code that does the calculations. And this solid line here is our model for the eclipse. So we kind of understand what's going on. Nice. We can model this part. We cannot model this one, though. And anyway, I can leave this for the questions if you want. It's a complicated thing. Anyway, that's not my last slide. This is my last slide, sorry. So when you take all your spectra that we observed in H-alpha, this is the so-called dynamical spectrum. So everybody knows what a dynamical spectrum is. Probably it's good to explain, right? A dynamical spectrum is you take one observation and it becomes a strip like this. So the color here indicates intensity. Yellow, very intense. Blue, not so intense. And then time is in the vertical direction. So each cut here, one cut like this is one spectrum. Another cut is another spectrum, right? So what we can see here from the H-alpha line? The 2 arms. Look at the 2 arms. One arm in one side of the star goes to the other side. One arm that goes to the other side. Cool, huh? These enhancements are the arms. These arms here, right? But then we discovered something very bizarre, which is we got some infrared by chance. I had a friend working at the SOAR telescope 4 meters in Chile, and he sent me a WhatsApp message and say, Alex, I have a half an hour for the triple spectrograph, which is very, very high resolution in the infrared. Do you want a spectrum? Yeah, take a spectrum of this guy for me. And he sends the information a few hours later. And then I sent this picture to my student, one of these spectrum here, and I sent him a message. This is your PhD smiling at you, right? Because he's going to have to explain it now, right? Because what we saw, it's a very weak helium line 10-830, in emission. But this emission is traveling back and forth 200 kilometers in one side to another per second. What this means is that this emission, very tiny emission, is coming from the secondary disk. So we saw the secondary disk in the spectra. So we could not see it in the visible though. But I don't know if some amateurs instrument can reach this line. Do you think it's possible? Very difficult.
The resolution of the spectrum.
Or the position of the slit, or the, I don't know. It's difficult, but this line is very important. Now we have an ongoing project where we are trying to identify more circumsecondary structures with that instrument. So far we saw just one. And this is the second case that I know where a circumsecondary disk was seen. The first one, it was in a paper 5 years ago, and I started called HD 55606. And that star, they saw it, the secondary, they didn't discuss it much, but in this case we could see it again, okay? And that's it. Thanks for your attention. Yes?
So, two questions. The first one is regarding the last...
Can you share your microphone maybe?
So I have two questions. One regarding... So one regarding this last slide, where you presented the performance of the helium lines, while everything else is H alpha.
Yes.
What about other H lines? Why you cannot, or what other H lines can give you, what kind of information give you regarding the performance of
Good
this
question,
line?
yes. Okay.
And the other second question is, you mentioned, I think, in one of the slides that the loss of matter is quite high. Well, you mentioned
It's high,
It's high.
and it's asymmetric.
However, I have the feeling that with such a big amount of mass and so many radiation, the stars should be depleted of mass in few years.
I can answer that.
Okay.
Okay, so the first question is, what about the other H lines, H beta, gamma, delta? They are extremely important, right? I didn't show this in this plot, but we use them. We have similar plots like this for the other lines. I didn't show them. And they are very important for one reason. So why H alpha is perhaps the most important line? Because it has what we call a large optical depth. And the large optical depth of H alpha means that the entire disk in yellow emits H alpha. So you are mapping the entire disk. As you go through beta, gamma, delta, epsilon, the emitting area decreases. Closer. That's why the emission is lower. And that is very important because you can study these different lines, you can map different parts of the disk. This is being done in this paper. So I didn't have time to discuss. Excellent question. So H alpha, it's not the only line. All lines are important, and the hydrogen series is extremely important for us, right? Because we can map the entire disk. Okay. The second question was about mass loss. Yes. So if you look at this, right? So okay, these or perhaps this guy, right? So mass loss is happening. The mass being lost, it's being lost it's for us humans. It's a huge amount of matter. It's 10 to minus 9 solar masses per year, which is about, I think, the mass of the moon every year. It's a lot of matter, but for the star it's peanuts. Nothing
I
happens.
thought it was higher.
Nothing.
One of the slides.
For the star it's not. It's like the sun. The sun is losing masses in the solar wind, but the solar wind is 10 to minus 14 solar masses per year. So you need more than the age of the universe for the sun to lose the entire mass. So it's not important. Okay. Oh, yes.
I was one of the observers for this project. I did H-alpha spectra a couple of years ago of the Northern Hemisphere stars, and I'll look forward to reading the paper.
Well, I can only thank you for the collaboration. You saw how important it is.
Yes.
Yeah, it is something that has never been done in this research before. Yes.
In the observations, you put this sequence of the spectrum of the H alpha. Is the is just
I don't know.
Yeah, this one. Correct, but why you have several spectra at the same time? This represents what? Because I just see only one, but there are 2, 3 simultaneously.
Yeah.
It's a technical one.
Oh, it is simply because we made this movie with a resolution of 1 day. So we show the previous spectra that all the spectra that shows in 1 day are shown. Okay. So some nights we have more than one spectra because this is phase, orbital phase. So it's many years of observations that you fold in phase. In some phases, sometimes you have many spectra, or many spectra nights. So that's why.
Could you say more about the test photometry data? Number one, what's the cadence of the photometry? And number two, how quickly can you see the data? How soon after?
Very good question. It changed over the years, the cadence. Initially, there were two modes. It was the 2-minute mode, so 1 point every 2 minutes. And then there was the 30-minute mode, 1 point every 30 minutes. And then they changed this after 2 years of operations, and now it's about 1 point every 10 minutes. So, and TESS, it's a very broad field, and it stays in that field for approximately 30 days. So that's why many times in that paper, for instance, you see a plot that goes from 30 days, right? In this case, it's 60 days, I think. No, it is, yeah, almost 60 days, because it's 2 sectors. What happens is that it moves, it points the telescope to one place and observes for about 30 days, and then it moves. Sometimes, if you are lucky, like in this case, the 2 fields overlap. You see, and then you have 60-day base. Then it's much better. If you had just 30 days, we would have missed this one, for instance. So the longer the better, of course. Yes.
I have 2 questions. On that slide, which you're looking at now, you see an oscillation in the VR ratio there. If we were observing that star with spectroscopy and the star was bright enough, would it be worth doing time series spectroscopy over an evening? And would we pick up that variation?
Yeah, that's exactly what we're seeing.
Yes.
Yes, because it's one day to another. You see, one tag here is 2 days. 2 days here.
Yeah, so
every tick is 2 days.
It's hours that is changing over timescales of hours.
One night. Yes.
Yeah. And the second question is that oscillation reflecting the speed of rotation of the disk? What you're actually seeing is, they say, symmetry going around that quickly.
I was told that I was going to get very good questions from the audience, and that's a very good point, because that's why I bring movies. Movies are useful to answer, right? So this movie, what is telling us, right? It's telling us that there is a point in the star. That's a model. It's a very spherical model, very simple model, right? There's a point on the star that's exploding and launching matter into the disk. And then there is the time scale of the rotation of the star. However, material, once is lost, it is not bounded to the star anymore. Now enter a second period, which is Kepler's law. Kepler's law. It is orbiting. It's free from the star. And then this material is going to have its own period that has nothing to do with the stellar period anymore. So our interpretation is the following. Here. Our interpretation is that there are stellar periods, that's things that are glued to the star, and those track the rotation of the star. And there are these periods that material that is orbiting of the star, and those have Kepler's law period, and those are shorter periods. Because these are the orbital periods, the red ones, that comes from the line. Very good question. Is there?
No. My questions, 2 of them. One first, what are requirements to the observational equipment in order to support some kind of observations? And second, it looks to me that you make a way of deduction your ideas. You have an observation and you're doing calculations, and then you compare your models to the observed phenomena. How does can Doppler tomography help in order to resolve a direct structure or some clumps or whatever in the disk?
Good. So the first question, can you remember? There was
requirements of the
requirements. Yes, sorry. Okay. So the requirements are more or less a signal to noise of about 30 to 50. Right, and resolution of 10,000, right? So these Some of the spectra that we're seeing here, not all of some of them are amateur spectra, and they have this 30 to 50 signal to noise and 10,000. It's plenty for us, right? Higher resolution is better in some cases, but 10,000 is enough for us. And now Doppler tomography. That's a fairly good question. I don't have a definite answer because Doppler tomography, they have never been attempted in the stars yet.
No.
That I know of. That's
We published some.
oh, in the Pie yes.
Not in the Pie.
No, but that
I will have this information in my talk.
I don't.
Yeah.
Anyway, there is not. So I've been trying to do this for over the years. I've never done it for lack of time, but I think you're going to have a definite answer for me. But I always thought it would be very nice, very important.
Unfortunately, you need a big amount of time resolved data at the end.
Yes, you need very good phase coverage. I would say very fine coverage. So let's have a proper answer in that.
Okay.
More.
Please, the last question because of time.
Quick question, is there any correlation in the pulsation with the magnetic field strength?
Very good question that I can answer very fast. So, one of the mysteries of these stars is that none of them is magnetic. So there has been a study. I participated in this study where they studied like hundreds of magnetic B stars. 10% of all magnetic stars are magnetic. No, sorry. 10% of all stars, massive stars, are magnetic. 10%. 0% of these stars are magnetic. So I think we have a few explanations for this, but so the rule is 0. That's
because of the mixing of the internal stars.
It could be the mixing. It could be the fact that they have very complex photosphere at their equator. So yeah, thank you.